Now, one of the things that you may have been scratching your head about earlier, and I kind of alluded to this, is if a curve asymptotically goes to zero, that means it never reaches zero. It just gets infinitely close. It's never actually equal to zero. Then shouldn't there be an infinite area under the curve? And we saw that when we integrated from 1 to infinity of 1 over x dx, we saw this be divergent. There was an infinite amount of area under the curve. But when we integrate from 1 to infinity of 1 over x squared dx, that equals 1. So there's not an infinite amount of area under the curve. And there are a lot of curves that are like that. So let's take a look at this particular one. I want to go from 0 to infinity of e to the negative x dx. So you know what that looks like. From 0 to infinity, this curve looks like this. Asymptotically, it goes to 0. When x equals 0, we're at 1. So I'm trying to figure out how much area is under the curve. Will there be a finite amount or an infinite amount? And one of the things I said earlier when comparing 1 over x to 1 over x squared was that 1 over x didn't go to 0 fast enough. And that's why we end up with the infinite amount of area under the curve, whereas 1 over x squared does go fast enough. So how would that compare to e to the negative x? So let's go ahead and integrate this. I have this improper integral because I have that infinite bound. So I need to take a look at the limit as b goes to infinity of the integral from 0 to b of e to the negative x dx, which equals the limit as b goes to infinity of a negative e to the negative x evaluated from 0 to b. And like usual, I have a negative. I'm going to pull it out and put it up front here. So this will be equal to negative of the limit as b goes to infinity of e to the negative b, which is 1 over e to the b, minus 1 over e to the 0. Well, as b goes to infinity, e to the b goes to infinity, so this goes to 0. E to the 0 is 1, so this is a negative 1, but I have a double negative, so this is actually equal to 1. Well, that's kind of interesting because that has the same area as 1 over x squared does. Therefore, this integral is convergent. It converges to 1. What about this function? I have both an infinite upper and lower bound. I'm going from negative infinity to infinity of e to the x over 1 plus e to the 2x. So what I need to do is break this up. So I'm going to take a look at this as the integral from negative infinity to 0 of e to the x over, and I'm going to write this as 1 plus e to the x squared dx. That just helps me see a little bit better what I'm going to end up doing here. And then I'm going to add that to the integral from 0 to infinity of e to the x over 1 plus e to the x squared dx. So now I need to take, to actually evaluate this limit, I need to, or this integral, I need to take two limits. So I need to take a look at the limit as a approaches negative infinity of the integral from a to 0 of e to the x over 1 plus e to the x squared dx. And I need to add this to the limit as b goes to positive infinity of the integral from 0 to b of, again, e to the x over 1 plus e to the x squared dx. Now, I'm going to ignore these limits for just a second, and I'm just going to work with the indefinite integral. So I need to find the antiderivative. Once I find the antiderivative, then I can slip it back in and work with these limits. So just for a moment here, I'm going to think in terms of the indefinite integral, e to the x over 1 plus e to the x squared dx. Now, this is just crying out for a u substitution. So let's let u equal e to the x, then du equals e to the x dx. So what I end up with is the integral of of 1 over 1 plus u squared du. Well, that we recognize right away is arctan of u. But u was e to the x, so what I really have is arctan of e to the x. So now that I know what I'm dealing with, let's go ahead and work with these limits. This first one would be the limit as a goes to negative infinity of arctan of e to the e to the 0 minus arctan of e to the a. Now this limit really wasn't needed in here because there's no a here. This is e to the 0. Well, e to the 0 is 1. Arctan of 1, that's saying when is tangent of theta equal to 1? That happens when theta is pi over 4. So this is going to be pi over 4 minus, well, as a goes to negative infinity, this e is actually 1 over, or it goes to 1 over e to the, I don't want to say infinity there, but e to the absolute value of a. So this actually goes to 0. So this is arctan of 0. So when is tangent equal to 0? And that's going to be, well, when theta is 0. So this first piece is going to be pi over 4 minus 0. The second piece, I'm kind of running out of room here, so I'm going to stick it down here. I need the limit as b goes to infinity of arctan of e to the b minus arctan of e to the 0. Well, as b goes to infinity, e to the b goes to infinity, and when is arctan equal to positive infinity? On the closed interval, negative pi over 4 to, negative pi over 2 to pi over 2. And that happens at pi over 2. So this is going to be pi over 2 minus e to the 0 is 1. And where I said, when is that? When is arctan equal to 1? Well, that's when theta is pi over 4. So I have pi over 4 plus pi over 2 minus pi over 4. The pi over 4 is going to cancel, and the answer is going to be pi over 2. So between negative infinity and infinity, this curve has a total area under it, a finite area of pi over 2. So this curve, or this integral, is also convergent.